All right, so we saw previously a little bit of what a telescoping series looks like, but now we're really going to apply some past techniques to express a series as a telescoping series using partial fraction decomposition. So the first thing I want to do is I just want to take a look at the insides. So I want to look at 2 over 4n squared minus 1. And I want to look at it under the lens of partial fraction decomposition, which means that I need to factor out the bottom. So I'll have 2n plus 1 and 2n minus 1. Or rather, let me do it the way that I did it in my scratch work so I can stay on track. Okay, boom, boom. So 2n minus 1, 2n plus 1. And by partial fraction decomposition, I know I can write this as a over 2n minus 1 plus b over 2n plus 1. And now I'm going to solve for my coefficients a and b. So if I multiply to clear out the denominators, I'll get 2 equals a by 2n plus 1 plus b by 2n minus 1, and then I choose my killer n values, I guess, since we don't have x's. So at n equals negative 1/2, the 2n plus 1, that goes away. So I would get 2 equals b times negative 2. So that would lead me to b equals negative 1. So I've got b. Now my other killer n equals positive 1/2. I would end up with 2 equals a times 2, b times 0. I'm not going to write that. So here, so here I would know that a equals positive 1. And so I'm ready to rewrite my fraction using my partial fraction decomposition. So we had 2n minus 1, 2n plus 1. I'm going to write the negative as just a minus instead of putting it in the denominator. So that's b, and then a was 1 using partial fraction decomposition. And so now what's nice about this is we can actually look at the partial sums and you'll have a nice pattern. So just in general, let me see how much space I have. Okay, so just in general, S sub n is going to equal 1 over 1 minus 1/3 plus 1/3 minus 1/5 plus 1/5 minus 1/7. So there's a pattern here. Plus dot 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 plus all the way into the end. So we'd have 1 over 2n minus 1 minus 1 over 2n plus 1. And so hopefully you can see that there's cancellation, right? So 1/3 and 1/3, 1/5 and 1/5, 1/7 and 1/7. There's a 2n minus 1 over here. So all these things cancel out, and what you're left with is that S sub n is just 1 minus 1 over 2n plus 1. So that's the benefit of doing the partial fraction, is that it leads us to a really nice form for our partial sum. So then if I wanted to compute the series from 1 to infinity of 2 over 4n squared minus 1, this is the same thing as computing the limit as n goes to infinity of S sub n. And we have a nice form for S sub n. So this is the limit as n goes to infinity of 1 minus 1 over 2n plus 1. And again, this is another straightforward limit. So 1 over 2n plus 1 goes to 0 as n goes to positive infinity. And so we're left with 1. And we say that the series converges. The next thing we want to look at is a formal treatment of the geometric series. So we saw an example, the first example had a geometric series in it, but now we're just going to go ahead and give a general case. So long as R is between negative 1 and 1, sorry, strictly between negative 1 and 1, so you could think of it like this, then this series will converge. And we don't care what this A is, it's just a coefficient. So as long as our R is strictly between negative 1 and 1, we know that the series converges. And furthermore, we have an equation or a formula for what it converges to. So let's look at the first series A. So the way that you can write this is n going from 0 to infinity, 3 times 1 over 2 to the n. And you might be thinking like, well, that's not really in the form that I need it. So we'll take it one step further. N equals 0 to infinity, 3 times 1/2 to the n. And the reason I can pull that n out is because the 1 on top doesn't grow exponentially. It'll just always be 1. So here what we're going to see is that R equals 1/2. And A equals 3. So we're going to apply theorem 9.6. So we get it's A over 1 minus R. So we know that A was 3 and R was 1/2. So if we go ahead and work this out, we'll get 3 over 1/2. So we should end up with 6. For the next one, it looks similar, but it's actually quite different. The 3 is being affected by the exponent. So in this instance, R equals 3 over 2. So since the absolute value of R is not less than 1, the series will diverge. So here's another kind of fun use of geometric series. So we're going to write the repeating decimal 0.08 as a ratio, and the way that we're going to get that ratio is we're going to use the geometric series. So 0.080808, etc. is actually equal to 8 over 100 plus 8 over 10,000 plus 8 over, what, 1,000,000? Etc. and so on. And so I'm actually going to write this as powers of 10. So this is 8 over 10 squared plus 8 over 10 to the 4th plus 8 over 10 to the 6th, and so on and so forth. So now I'm ready to write it as a summation. It's 8 1 times 1 over 10 to the 2n. And notice that we're going to start from n equals 1 to infinity. This is important because in our theorem for 9.6, it's really, really important that this formula applies when you start from 0. So that's super important. But we're not starting from 0 in this example. So we've got to do a little bit of an adjustment. So if I start from 0, let's think about this. If I wanted to start from 0, I would be adding an 8, right? Because at the 0th term, if I start at 0, I am having 1 extra term. So I'll have to subtract the 0th term to compensate from that. And the 0th term is 8 times 1 over 10 to the 0, which equals 8. So what I'm going to do is I'm going to just have my standard form for geometric series. And I have to peel off an 8 at the very end. The other thing that's worth noting is that I have to rewrite this a little bit. 8 times 1 over 10 squared to the n. So now I have it in the form that I need. So here we have that r equals 1 over 10 squared, or you could say it's 1 over 100. And we also have that a equals 8. So what we'll get for our final answer is a over 1 minus r. And don't forget to subtract an 8 at the very end. So we're going to get 8 over, let's see, 99 over 100 minus 8. Oh my goodness, so this is 800 over 99 minus, let's see, what's 8 times 99? Minus 792 over 99. And then what we'll end up with is just 8 over 99. And so this is your final answer.